All right, everyone. Welcome for this session on Friday afternoon. I know it's a bit late and it's almost like weekend, so I'll make it easy and make it fast as well. I'm going to speak in English, obviously, because this is quite important topic in general. Feel free to take some screenshots or some photos from these slides to just better understand what we're trying to do here. Initially, when I planned this to stream processing, and I wanted to make it easy to understand and also easy to work with, because every time you hear about online applications in general, the fact is that using your mobile app now, the chances are 8 out of 10 apps are using real-time stream processing in it. So this is a quite important topic, and we need to know things, right? So what are best practices? And essentially, we're going to use microservice architecture today. That some of you heard of microservice or know what microservices are, but we will see in action how you can basically take from development and put it into production, because there is big gap. So many factors can go wrong. So my name is Fawaz Ghali. I lead DevRel at a company called Hazelcast, which is unified data platform for stream processing. And I had this discussion with someone about how fast is fast. So basically, this person created a mobile app, and essentially it took him to load this application. So as soon as you click on the mobile icon, it takes roughly around 3 to 5 seconds, right? So we were discussing if that's fast enough for him or not. And he said, like, his clients are quite happy with it. So there is nothing wrong, waiting 2 or 3 or 5 seconds to load the application. So I asked him, like, how many users do you have? And he said, on average, he expects to have 10K or 10,000 users per day. And he is quite happy with it. So he has auto-scaling with his app, and his architecture is microservice. So I asked him, like, what happens if we just try to reduce it to 1/10 of this value, which is like roughly around half a second. And he said that's not possible. And essentially, we had this discussion about what is possible and what is not. So for today's session, what I want you to think about 2 different types of data. So we're not going to discuss just batch data, but also we're going to discuss what is real-time data and how you can use it to your advantage. So just to make it more interesting, do you know how fast it takes for a, I think I need just to, right, so you know how long it takes for a Formula car to accelerate from 0 to 60 miles per hour on average? Any guesses? 2 seconds. 1 second. Right, so yeah. So the answer is sub-milliseconds, right? So it's roughly 2.5 seconds, depends on the model and so on. So your answer was around, and my answer was on average 2.5 seconds. So if you look at the answer here, we didn't say it is 2 seconds, or we didn't say it is 3 seconds, right? So we said around 2 seconds or 1 second or around 2.5 seconds. So we're trying to measure time in sub-milliseconds, and this is crucial. It's not the same as, for example, you acquire your database and you try to load your transactions or events from database, and you say, okay, I don't mind, I'm gonna go and drink a cup of tea or a cup of coffee and come back, I will get my results. So the story is different here. And you might be wondering now, you're not working with Formula 1 or you're not interested in Formula 1, so why do you care? And the answer is simple here. So essentially, everywhere you go, it doesn't matter what you do, whether you are a developer or data scientist or machine learning engineer, or even end user, right? Which is like most of us here are end users for real-time applications. Now, if, like, I ask you to open your mobile app, now roughly 80% of 10 apps are using real-time in it. So think about it as in terms of banking, so payment processing, for example, frauds. If you look at it in IoT devices, smart cars, for example, or if you look at hospitals, machine learning, and even sports. So essentially, it's everywhere, and it doesn't matter if you're using it or not in your work. The chances are in few years or few months, you need to basically shift between these two application types. So there is a concept here called time decay. Essentially, time decay means the longer you wait, the less value this information has, right? So it doesn't matter if you're dealing with real-time applications or stream processing. If I ask you what you did last Friday, right, compared to what you did last year, if you were in this conference, for example, last year or 2 years ago, the chances are the sooner these events are, the more memory you have, because it has more value in it. And same thing for any type of applications, right? So essentially, if you think about it, if this information has time to value of 1 minute, it's more valuable than 1 hour. And same thing, if it has sub-milliseconds, it has more value in it. So I want you to basically move from something called batch analysis into something called real-time analysis, right? So batch analysis, essentially, you read your data, you ingest it from somewhere, and then you load it into your database, right? Or file system. Then what you do next is you load it back again from database into your application or into memory, and you do some kind of analytics on top of it. And maybe you do some kind of visualization, right? So this is called batch. And even if you move to OLAPP or OLAP applications, where you do some kind of stream processing on top of your batch, it is a slow process. It's not fast. And we define fast by sub-milliseconds here. In fact, it is real time if you manage to process it before you store it into database. So let me repeat it again. The goal from this session is to be able to process data before we store it to database. Of course, if you move in this direction here, you see it on the screen, you add more value as soon as you basically process it. So whether you do machine learning on top of it or not, the goal is to get to the concept of real-time application. Now, if you think about your current job, right, and your current use case or your current task or whatever you're working on now, the chances are that you have some kind of perfect solution, or at least I hope that you're working towards this, right? So you're trying to do the best out of this, whether it's a performance, whether it's a code, whether it's accuracy. I don't know what perfect means to you, but essentially you have a perfect application, right? But always there is a but into it or attached to it. So in some cases, this but means, I don't know, like I know the average of how many transactions I have per day or per week, right? So this is kind of like a counterproductive because this is just the average. And the average doesn't mean anything, right? So if I ask you now, how many transactions you received into your application last week, you know the answer, right? So you go to your database, you say select count from a database based on last week, you get the answer. So this is fine, but what about data spikes? So data spikes, you don't know what spikes are, right? Because it's called spikes, and usually it happens in the future, not in the past. You might have some ideas. So for example, if you create a web application and you have some events like Black Friday, for example, you might have 10 times more than average. And this is kind of like, it can break your application. And it can break it in terms of delay, or even worse, when it provides some kind of false positive or false negative into results when you do analytics. So this process from having a use case to getting results is not straightforward. And this is crucial to understand, because as soon as you take your product, your application from development into production, you will run into some issues. So for example, how do you actually deploy your application, right? You might say, okay, I will use this cloud provider, put it on multiple regions, for example, multiple AZs or availability zones, and it should work, right? So that's automatically. That's not accurate, right? You know that's the way to proceed, because first, we don't know where your data is coming from. And second, even if you put auto-scaling or if you enabled auto-scaling, we don't know how you can monitor your performance, your application performance. So what we want is to have full control on the application when it's in production, right? And for this mission-critical applications, we need to think about it as two different types of data. So we have real-time data, and real-time data means basically you have some kind of Kafka topic, for example, or Amazon Kinesis or Apache Pulsar, where you ingest data into your application, and this has happened in real time. But instead of taking it from Kafka, storing into database, and loading it back again to do some analytics, we need to process this as soon as it arrives. Not only this, but also we want to provide some kind of historical approach to it. And now you might be wondering, why do you need to do it like this? Why not only use real-time data to do stream processing in real time, right? After all, real-time data should mean that you should be able to do stream processing in real time. You get real-time data, you do stream processing in real time, right? And that's the mistake for these type of applications. Usually, you can process the data, so you can say, I can do data transformation on my data in real time. I can do some calculation. But you don't know the context for sure what's going on with your data. I will show you an example today how you can basically see benefits of historical data for real-time data. Now we're going to use microservices architecture for this type of applications today. I'm sure you had some sessions today, or maybe you heard of microservices before. So I'm not going to spend much time on this. If you're new to microservices, microservices are great, right? I want you to start basically working with microservices if you haven't done so. And if you're already working with microservice architecture, maybe you move to something called event-driven architecture for this type of mission-critical applications. So this allows you to actually to manage your application in much easier way. So basically easier to deploy. You split your code into multiple pieces or multiple classes, however you want to call microservices. You place it in various locations for various microservices, and then you should be able to scale. So now if I ask you now, okay, let's take your application for example, and it's not microservice based. And I ask you how many transactions, you say it can handle 1,000 transactions. Say, okay, we're going to change the requirements today. I want you to be able to handle 10,000 transactions, so 10 times more, right? You changed your infrastructure, you changed the deployment, and it worked, right? But if you have, for example, 3 tasks, so one task is read, one task is process, and one task is write, what you ended up with is basically you scaled everything, whereas you should basically be aware what you need to scale. So you scale, for example, read separate from process or separate from write. And notice I said scaling, and if I ask you now what scaling means to you, right? So for some of you, scaling means I want to scale my architecture, so I want to scale compute or performance or hardware, memory, and so on, cluster and nodes. And some of you might say, no, that's not the right answer. The right answer, I want to be able to scale my data, right? I want to be able to handle 10 times more or 20 times more. And essentially, you need to be able to actually combine between the two. Because the right answer is combination between the two. Why you need to combine between scaling compute as well as scaling data? Because the game here today is to minimize latency, right? So think about it as 4 nines or 5 nines. So instead of saying I want to have latency of 99.99, I'm going to say I want to have a latency of 99.999, so which is basically sub-milliseconds latency and 99 or 5 nines availability. So this is crucial because if you have two data centers, now auto-scaling, what it does for you if you use like cloud auto-scaling, is actually increase number of clusters, increase number of nodes within clusters. Maybe you say I want a region in the US or region in Europe, and it scales, but it doesn't look for your data. It's just to scale the compute. But here we're taking it a step further. We want to be able to store data as close as possible to our microservices. So think about it. If I have a microservice here in Portugal, for example, and a microservice stored in a data center in the UK, I want you to be able to have your data related to microservice in Portugal data center, and likewise the data center in the UK, the data should be relevant to the the data center in the UK, because there are some network hops or read and write which slows down your application. So for microservices, there are three ways to do it. So I'm not going to explain how you write microservice. I'm going to explain how you deploy it into production. So first way to deploy microservice for large-scale applications is to use something called embedded mode. Essentially, if you work with Java, for example, you include a jar into your POM file, and essentially you have it embedded into microservice, and this is connected to the cluster underneath. So this is one way. I have the same structure today for today's demo. Now, second way is to change it, to make it client. You use the embedded if you care about latency. So banks usually, or financial institutions, use some kind of embedded solutions, not because it is the best way to do it, but because they want to minimize latency. Now, for other type of applications, for example, retail or online shopping, they use something called client mode, which is basically dislocating between your microservice and your infrastructure. And this allows you to handle spikes because it allows you to scale your compute regardless of how many microservices you run. And the third way is combination, and this is something that might be new to you. It's called a pipeline. So essentially, you have microservice or more, you have your cluster with one or more nodes, but you ended up using a pipeline architecture. I'm going to show you what pipeline is. Those who are familiar with Java, there is a function called Java Lambda. So Java Lambda allows you to run multiple commands in parallel in one pipeline. So exactly, basically as pipeline as steps of this type of architecture. We were going to use for today's demo Kafka. So if you're new to Kafka, Kafka is great to use it as message bus. So you move your data from A to B, and it is really good if you even want to do some kind of simple stream processing, because if you remember what we talk about real-time stream processing, Kafka allows you to do stream processing on the real-time data. But today we're taking it a step further, right? We don't want just to process the real-time data, but also we want to process the historical data. So let's just take this example today. Imagine that you want to take some money out of your bank account, right? So you go downstairs, there is ATM. I'm not sure how much they charge for that ATM, but think about it. You put your ATM in the your card in the ATM. You put your PIN code. This request goes to your bank. They validate it and say, for example, I want to get 100 euros or whatever. And if you have enough money, they send the acceptance, and finally you get a response, right? So there are 4 or 5 steps attached to this. First is to ingest the data. And ingesting data means reading your card details. So what is your card number, for example? What is your PIN code, and so on. And now this is the part I want you to understand, and which is the historical data. Now this historical data doesn't come from your card. Basically, it comes from your bank account. So for example, how many transactions have you done last week? Where are you based? Where is your bank based? And what is the GPS coordinates for your ATM? So all these elements are called historical because they don't change over time, right? So yes, they change, but they don't change in real time. And once you have the real-time data and the data enrichment for batch data, you do some kind of data transformation. So those who are familiar with machine learning, you do some kind of normalization, for example. You change type of data, you select features, and so on. And then you do something called machine learning in real time, which is completely different from the traditional machine learning. So machine learning in real time means you constantly update your model all the time. So you don't just train your model, put it into production, and forget about it. You constantly change it over time, and then you get this response. So it took me like 3 to 5 minutes to explain this process. How long do you think banks usually respond to this request? Very quickly, yes. So yes, they have very short SLA, which is around 50 milliseconds, or let's just say 100 milliseconds. So that's 1/10 of the second, right? And we need also to add on top of it the network hops or delays in read and write and everything. So if there is a fraud, by the time I say fraud, your bank already decided if there is a fraud or not, right? So if I say now fraud, it's already been determined if this transaction is a fraud or not, because yeah, I said it's slower than actually getting this confirmed. And this is only part of the story, right? Because there is false positive attached to it and false negative, for example, attached to it. So for example, false positive means it's basically you who's taking money out of your bank, but your bank say, let's start declining because it's a fraud. So this is one example of doing it. Now there are two ways to proceed from here. So if you think this is important topic, and I hope you do, regardless what tool you use or which framework you use, the job market is changing. So we're moving away from batch jobs to real-time jobs. So it doesn't matter which company, even if they're not using real-time, at this moment the chances are at some point in the near future they need to actually have real-time responses. Even if we look at normal, small companies, they need real-time element in it because they realize basically the value attached to this information. So there are two ways to do it. So first way is we call it DIY approach, and this is basically you do it by hand, right? So it as you have job at your home. Let's just say plumbing job. Your tap is leaking, for example, or your lights need fixing, and so on. So this is DIY, right? You go somewhere, DIY store, you buy your tools, right? And you go home, and then you try to figure out how to fix it. You open YouTube, and you start learning, and by the time you finish, it's almost nighttime, so you put it till next day, right? So the main reason I'm explaining it this way to tell you, first, there is a learning curve, which means every time you add a new tool, you have to learn this tool, right? And it takes time to learn. Doesn't matter if you use real time or not. And secondly, it takes time to deploy and develop. And third part is basically how you maintain it, right? And what happens if you left your house, who's gonna maintain it after you leave, and so on. So many elements. Now if you go to the exhibition center and you look for jobs, for example, I bet 60 to 70% of jobs currently are just because of legacy teams. So legacy teams means you have a situation or use case, you hire a team, they create a solution, and they move on, and you get stuck for maintaining this code. So this is exactly what happens if you follow this approach. So you ingest your data from Kafka, AWS Kinesis, or Amazon Kinesis, Apache Pulsar. You use Flink for stream processing. You use Redis for fast data store, for batch data. You use Feast for online feature store for machine learning in real time. And you use some kind of databases along the way in order to do everything. So now we want to simplify it, and I want you to simplify it. I want you to think about it, how you can save not only time, but also how you can save in terms of latency, right? Because latency is the key. So let's just look at a different way of applying this. Essentially, if you look at large companies now, I want you to go home and search your favorite company. I'm not going to name because it's been recorded. So go home and search for large IT companies, right? And look what they do. What they do is essentially strange, because you think about it, they have inbuilt solutions, right? So they basically create solutions from scratch. Why they do it this way? Why they don't use, X tool for their pipelines and so on? Simply because they realize if you develop inbuilt solution, basically you're able to connect multiple frameworks or multiple tools, and this will minimize latency, right? And this is what Hazelcast does in real time. Basically, you get two components, which is stream processing and fast data store. You connect whatever clients you want to do and whatever programming language. My background is in data science, so I like to use SQL. I encourage you to learn SQL. And you can use SQL to do stream processing in real time. Of course, you need to handle security. So regardless if you use real time or not, I want you to think about security in two aspects, even for your applications. Just forget about stream processing. You need basically to attach security to data at rest. So this is kind of like KMS. And you need to attach security to data in motion in real time, which is basically you apply HTTPS on top of it. And to do stream processing at scale, we need to be able to connect, machine learning models. Obviously, this is optional. But if you think about machine learning, you need to run your machine learning models on top of Python virtual machine and your application on top of Java virtual machine. So now, don't ask me after we finish this presentation whether you should use Java or Python. I can explain it outside, but the final answer here is Python for machine learning for deployment and production, and you use Java for enterprise applications. So let's just say what we want to do is basically to do stream processing at scale. So this will explain the architecture. So in here, I'm ingesting my data in real time from Kafka. I'm loading it to my cluster, which has nodes. And then I'm actually enriching this from different map architecture. So map is just key value pairs. So in order to run it, you need basically to have a cluster. You can host it on the cloud, or you can host it locally. So let's just jump quickly and show you the code here. So this is Java code here, right? If you don't know Java, that's fine. Basically, you need a library to attach it to here, to your code. So I'm not going to ask you to change your application. In fact, you can take any application and put it in real time. So in order to do it, you need obviously to have either embedded or client architecture. So in my case, I'm using the embedded architecture. So I just need to have the library for Hazelcast and the Jet engine. So let's just generate some data here in real time. So you see these actually events are coming in real time. So let me increase this screen here. So 48, 50, 52, 45, and so on. So this is not coming from database, and it is not for loop. It's not loop, and I'm counting. It's basically events are actually coming into Kafka topic, and I want to process it. So if I show you my code to process this data, so now, again, if I ask you how many transactions you have in your database, you know the answer. But for real-time data, you don't know the answer. Maybe you know where your data started, but you don't know where it ends, right? So what you need is to apply windowing on top of it. Windowing means you specify window size and you say I want to basically shift it based on time frame or based on number. And I create this to read from the Kafka topic. So here, if I run my application, you see I have these numbers I want you to track. So I have 5, 4, 3, 2, 9 events per second, 4, 3, 6, and so on. So, but what does it mean? Is that really stream processing? The answer is not. So even if it is stream processing for real-time data, but I want to enrich it, I want to add value into it, right? So let's just switch to SQL and show you how we can do it. So for the SQL here, there are 4 elements in it. So on the left side, I have Kafka running. So this is the Kafka Zookeeper, and this is the Kafka server. So just for messaging, I have Hazelcast instance running, and I'm gonna generate some data, right? So this is my stream here. Now, if I acquire my stream, so which is basically give me all events which marked as event 2. Let me increase the size so you can see. So I'm gonna say give me all events where these events are just flagged as event 2. So it's basically microservice 2 or customer number 2 or user number 2 and so on. And now this is exactly what we saw before on the Java or IDE. So you see event 2, you see the number of it, and you see the amount. Now I want to take it a step further, right? I want to be able to enrich it in real time. So in order to do it, we first need to understand this, how we can achieve it, right? So if we go back to the code here, we actually create map structure, right? So map is just a structure, you store it into memory. It has key value pairs, and basically it allows you to fast process your data. So you need to have 2 maps in general. First map is for the real-time data, and real-time data, like I mentioned, coming from Kafka, and second map is for the batch data. So this is the batch data here. So in SQL, I'm saying I need to create new map, and I'm gonna add 3 features into it. So I'm calling these features extra 1, extra 2, extra 3. So think about it as a fraud activity, for example, or think about it as online transaction, and you want to flag specific elements in the real-time data. Now, in order to store this data, now instead of storing the data into database or loading it back again, there are 2 ways to do it. So something called lazy loading. So lazy loading, essentially you go to your cache and memory, you check if it exists. If not, you retrieve it and you store it into cache, and then you retrieve it, and every time you update the value. And there is write through. So essentially every time you update the value, you update it alongside in the memory. So in this case, we're gonna store some events into the database, and now we're gonna change this. So we're going to do a real-time plus batch processing at the same time in one command or one process. And this is running, still running, so even I stopped it. So now if we check it again, you see the values are actually coming, still coming. And remember, these are generated in real time. Now, if we stop it here and we do the data enrichment, let me copy this one here. So this command says I want to select data from 2 maps, and at the same time I just want to flag specific elements or specific events. So in my case, I just want to flag elements which is extra 2 when it is only red. So if I run this command here, you will see the values actually on the screen. This is happening in real time, right? And this allows you to actually flag specific events in your process, whether it's like extra features or, for example, features coming from database or your file system, in order to provide the context. So the context in this case, basically just when the extra 2 or feature number 2 is read. Now if we stop it now and see how it works for machine learning, you need basically to define trends for your data, right? So let me explain the architecture first, and then we can proceed to see how it works. So the architecture in simple terms, every time you load your data, basically you read it and you store it into map, you can create a trend. So those who work in machine learning could be linear regression or decision tree, it depends what type of data. And you store this trend into map, which means you store it in memory. And you can use this trend in order to predict the future events. The future events will be actually stored in different map. So this is the prediction map now, which is basically where the real-time stream processing happens. And as soon as you have prediction map, you can actually store it back into the first map. So if we look at the code here, the code is quite simple. So in my case, I'm creating a source. I'm using a map journal because I want to be able to do the stream processing. And then I'm defining stream stage, like similar to the window concept. And from here, I define my trend. In my case, I'm using linear regression to be able to predict what's going to happen in the next value. So what is the score? And from there, I can actually output it to wherever I want. So the visualization part can actually be either on your application, so you can store your results into file, or you can send it back to Kafka or even web app. Now everything I mentioned today up to this point is the features of combining real-time data and batch data in one process, right? But the beauty of this type of application is to be able to connect two real-time applications, which is like even I would call it advanced, which allows you to basically combine and merge between two streams. So I'm not gonna spend much time because it's quite advanced. So if you're interested about it, or come grab me afterwards. But I want to show you to you so you understand what stream-to-stream joins is. So stream is, as I mentioned, like flow of data. And stream-to-stream joins allows you to merge or combine two or more streams in one stream. So you take two different streams in real time and you do the exact same steps as before. Obviously, you need to define time interval on it, and from there you can actually proceed to decide what type of data aggregation you want to do on top of it, whether it's, for example, counting, filtering, and so on. And as soon as you have the data, obviously based on the time frame, you can actually proceed to send it back to Kafka or save it into database. So that's pretty much what I wanted to cover in this session here. It's quite important topic. Takeaway messages is, first of all, spend some time to understand what real-time applications are and how you can basically create a real-time application. So this is really crucial to advance your career. As soon as you have this knowledge, I would say think about it in terms of what are the steps, what are tools you need, and always think about how long it takes, especially with this time and age where every day there is a new tool. You don't want to end up with like a one application which has 10 tools where you have the option to have like less tools. So that's second option or second takeaway. And third takeaway is to focus on performance. So I had stream processing at scale. So I ask you now how many transactions you have in your database, or how many transactions you process in your application. And like most applications you see online, they have not only millions, but they handle billions of events per second. So let's just grasp this concept. So 1 billion transactions per second with latency around 30 milliseconds or less, that's quite a challenge to do it in terms of applications at scale. So that you want to basically, every time you work with these type of applications, to not look how accurate your machine learning model is or how perfect your application is, but how low your latency is. So we run Twitch sessions. So this is live coding sessions. Feel free to join Twitch if you are on Twitch. It's just live broadcast, and you can get access to engineers and solution architects. So with that being said, thank you so much for listening. Hopefully it was useful, and let's just get some questions here. Thank you. Let's just, yep. Ask me a question. I'll repeat it. Yeah, go on. So the question is if there are some books or videos about it. I would say if you go to YouTube on the Hazelcast channel, there are some videos for stream processing in real time. And also there are some PDFs that you can download and get started with stream processing. So this is an option available on the YouTube channel. Yep. More questions? Right, I'm gonna stay outside. If you have any specific use case or you want to discuss anything about machine learning or stream processing, come grab me afterwards. All right, thank you so much for listening. Thank you.